Number one, graph the function f of x equals 2 to the x, and hopefully you realize this notation means the inverse of f. That's the inverse of f on the set of axes below. So use your graphing calculator to graph 2 to the x. You should be able to do that pretty quickly. 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 1/2, a quarter, and it gets really close to the x-axis but never touches it. And then draw in that nice, lovely exponential function. There is f of x right there. And remember, our big idea during this unit is to find the inverse of exponential functions, because we're going to use those to solve equations. So, to find the inverse of any function, we reflect it over the line y equals x. We say, what's the image of that function after I reflect it over the line y equals x? That's how we find the inverse. So the point 0, 1 becomes the point 1, 0. We take xy and map it to y comma x. We switch the x and y's. 1, 2 becomes 2, 1. 2, 4 becomes the point 4, 2. 3, 8 becomes 8, 3. Negative 1/2, that's negative 1, 1/2, becomes 1/2, negative 1. This is the point negative 3, 1/8. So 1/8, negative 3. Notice how that horizontal asymptote line now became this vertical asymptote. Here on the original function, I can never touch the x-axis. On this inverse function, I can never touch the y-axis. That point's too far over. I graphed that point wrong. Don't do that. Graph the right points. And then we draw on that nice, beautiful function there. We draw on that nice, beautiful function to find the inverse. So this red function here, after I erase the excess, is the inverse function. So make sure you label that f inverse of x. Explain why the function f of x equals 2 to the x has an inverse. Well, for any function to have an inverse, that function must be 1 to 1. It must be a 1 to 1 function, which means our y values don't repeat. We don't have different inputs have different outputs. And we notice that this purple function, the y values never repeat because it passes the horizontal line test. Our two different inputs never go to the same output. So that makes it 1 to 1. Functions have inverses that are functions if it's 1 to 1. So make sure you recognize this graph. This graph here is going to be very important in the future, this red function that we just made. That's going to be a very, very important graph that we study because that's the inverse, apparently, of an exponential function. Does the function h of x equal negative absolute value of 2x minus 1 plus 4 have an inverse? Explain your reasoning. I'm going to pull up my graphing calculator. So on my graphing calculator, I'm going to graph the function h. A function has an inverse if it's 1 to 1. So is h 1 to 1? Well, it has an inverse, but we want the inverse to be a function. Otherwise, we don't really care about the inverse. So let's go graph it. Let's go to y equals, and we need the absolute value function. And hopefully from 9th grade, you remember the absolute value functions in math. Scroll over to number and ABS of 2x plus 1. And then what was on the outside? Plus 4. So when I hit graph, we should look at this beautiful absolute value curve here. And is this function 1 to 1? Does it pass the horizontal line test? No, it doesn't, because I hit it more than once. Different inputs have the same outputs. Our y values repeat. So you should know that absolute value functions, that family of functions, are in the shape of that v. They have that corner there. So does h have an inverse? No. H is not 1 to 1. So its inverse is not a function. Then we can quickly sketch a little graph of h. It's an upside down absolute value function. There's h of x. That's it. Does it have an inverse? Well, we have to see, is it 1-to-1? Assume that g is an invertible function, so g has an inverse. If the point 73 lies on the graph of the function g, what point must lie on g inverse? Well, to find the inverse of a function, we reflect it over y equals x. And to reflect a point over y equals x, that takes x comma y and maps it to y comma x. We switch x and y. So 7,3 is on g, which means 3,7 is on g inverse. That's it. Explain your reasoning. You should say something, write a sentence or two about to find the inverse, we reflect it over y equals x. And finally, number 5, the graph of y equals h of x is shown below. Graph, you need to recognize this is h inverse, the inverse of h. Well, to graph the inverse, we switch our x and y's. We reflect it over the line y equals x. So this is the point -7, -5, which means when I graph the inverse, I'm going to go to -5, -7. This point here is 1, 3. So to graph the inverse, I'm going to graph 3, 1. And finally, this is the point 7, 5. It's over 7 up 5. So the inverse is 5, 7. Need to scroll up a little there. Inverse is 5, 7. So the inverse is this function here. Notice how that function is the inverse is the reflection over the line y equals x. Finally, we need to state the domain and range of h and the domain and range of h inverse. So remember, the domain of a function, well, let's label the black function h and the green function h inverse. The domain is our inputs, it's our x values. Well, the lowest my x values go are -7, and they go all the way until 7. So the domain of h, I'll do it over here, the domain of h is -7 to 7. And we use the square brackets because it's included. Those points are included in the domain. The lowest I go is -5, the highest I go is 5, so my range is -5 to 5. For h inverse, the green function, now how low do my inputs go? Well, they go from -5 to 5. The domain of h inverse is -5 to 5. The range of h inverse, well, how low does it go? -7 to 7. Notice how the domain and range switched when we did that reflection over y equals x. So when we find the inverse function, what we're really doing is we're switching the domain and range. We're switching our set of inputs with our set of outputs, and that's how we create the inverse function. So hopefully you found this helpful and understand graphically what we do when we find inverse functions. We switch x and y because they're reflecting over the line y equals x.